Okay, now we're going to run through some problems that are associated with crystal structures and the type of unit cells and the things that we can calculate using things like edge length and volume and densities. So the first problem is potassium crystallizes in a BBC, which of course is a body-centered cubic lattice, and has a density of 0.856 grams per centimeter cubed at 25 degrees Celsius. The first question is, how many atoms per unit cell? So if you recall, in the body-centered cubic cell, we have 8 corner atoms, of which 1/8 of that sphere is within the unit cell, plus one whole sphere in the center of the cube. So we have a total of 2 potassium atoms in a unit cell. The second question asks, what is the length of a side of a unit cell? So remember, these are cubic unit cells, and the edge lengths are A. So we can calculate volume of this cube by multiplying the edge lengths. So volume equals A cubed. Okay, so we are given the density of this unit cell, or potassium, here, and it again is 0.856 grams per centimeter cubed. And that tells me that this also equals the mass of 2 potassium atoms divided by A cubed. So remember, density equals mass divided by volume. So we need the mass of 2 carbon atoms. We already have the density because we can actually solve for A cubed here. So if we rearrange the density equation, we get V, or in this case, A cubed, equals mass divided by density. So we need to determine or calculate the mass of 2 carbon atoms. And so mass of 2 K atoms is going to equal, I'm going to write it down below, 2 atoms of K times the molar mass of K. We need Avogadro's number. 1 mole of K contains 6.022 times 10 to the 23rd atoms. So our moles of K will cancel, our atoms of K will cancel, and we'll get the mass of 2 carbon atoms as a result. And that mass equals 1.298 grams, need my exponent here, times 10 to the negative 22 grams. So that equals the mass of 2 carbon atoms. So we have that, we have our density, so we can solve for A cubed. So we take our mass, and this should be 3 sig figs, 298 times 10 to the negative 22 grams. We're going to divide that by our density of 0.856 grams per centimeter cubed. And so A cubed equals 1.52 times 10 to the negative 22 centimeters cubed. So remember, edge length is A, so we need to take the cube root of A. So 1.52 times 10 to the negative 22 centimeters cubed. And we're going to raise that to the 1/3. And A then equals 5.34 times 10 to the negative 8 centimeters. And it's customary to express these edge lengths in picometers. So I'm going to convert that to picometers. And in 1 centimeter, we have 1 times 10 to the 10th picometers. So we have an edge length of 534 picometers. Now we would like to determine the radius of a carbon atom. And for the BCC cubic cell, 4 times r, which is the radius, is equal to the cube, the square root of 3 times A. And of course, this is A equals edge length. And so we can solve for r, which is the radius. Okay, so r is the radius. And so if we rearrange to solve for r alone, we have A times the square root of 3 divided by 4. We just determined our edge length of 534 picometers. And we're going to multiply that by the square root of 3, divide by 4, and we get a radius of 231 picometers. So in this problem, we are not told what type of crystal lattice or cubic unit cell we have, but we're given an edge length and the density of solid iron. And we're asked how many iron atoms are within a unit cell. So that means we can use this information to determine how many atoms are present in a unit cell. So the first step in solving this problem is to calculate the mass of iron. In the unit cell. So we have the edge length and we have the density. So remember, density is mass divided by volume, and volume is going to be A cubed. So we have A cubed. And I'm going to start with, so this is A here, our density, 7.87 grams of Fe per 1 centimeter cubed, and I'm going to convert that to picometers so I can cancel my length units of length and end up with units of mass only. You can either do this directly or stepwise as I'm doing, but either works. There are 10 to the second centimeters in 1 meter. And I want to cube this. And then in 1 meter, I have 10 to the 12th picometers. I need to also cube this. And then I have an edge length of 287 picometers, which I will also cube. And that allows me to cancel all my units of length, and I remain with a mass unit in grams, and this is 1.86 times 10 to the negative 22 grams of Fe per unit cell. Okay. So, second calculation, I calculate the mass of 1 Fe atom. So, in order to do that, I need the molar mass of iron and I need Avogadro's number. And 1 mole of Fe then contains 6.022 times 10 to the 23rd atoms of Fe. So this will give me the mass of 1 iron atom, and that is 9.27 times 10 to the negative 23rd grams of Fe per atom. And the third and final calculation then is to calculate the number of Fe atoms in the unit cell. And I do that using my solutions to the first and second calculations. So in order to set that up, we want to get rid of the masses of iron, and we want to end up with units of atoms per unit cell. So I have to orient these two solutions such that my grams of iron cancel and I have atoms on top and unit cells on the bottom. So I have 1 atom, because I want that on top, has a mass of 9.27 times 10 to the negative 23rd grams of Fe. And I want the unit cell on the bottom, so I have 1.86 times 10 to the negative 22 grams of Fe, so I want to cancel grams, per unit cell. So these grams are canceling. I end up with units of atoms per unit cell, and when I do that math, I get 2 atoms per unit cell. So that corresponds to a body-centered cubic cell. This is the last example problem we'll do for these types of problems. You will encounter these in your sapling homework assignment. I will not be testing you on these, but you do need to have been exposed to them, and thus you'll have them in your homework. So in this problem, europium crystallizes in a body-centered cubic cell. We're given the density of that element, and we're asked to calculate the edge length in, that should have been lowercase, picometers. So we know that a body-centered cubic cell contains 2 europium atoms. 2 atoms. And the mass then of the cubic cell will equal the mass of 2 europium atoms. So the first thing we're going to do is calculate the mass of 2. Mass of 2 europium atoms. And we've done this just a moment ago. We have 2 europium atoms per unit cell. And in 1 mole of europium, we have 6.022 times 10 to the 23rd atoms. So we're getting rid of atoms, we're converting to moles, so we can use the molar mass to determine the mass of those 2 atoms. Mass of europium is 152 grams of europium per 1 mole. So we've canceled atoms, we've canceled moles, converted to grams of europium per unit cell. And this is 5.048 times 10 to the negative 22 grams of europium per unit cell. Okay. Second step, we're going to calculate the volume of the unit cell. Now, why are we going to do that? Remember, V equals A cubed, which is the edge length cubed. So V, the cube root of V, or A cubed, will equal A, which is our edge length. Okay, we have the density. All right, so we have our mass of 5.048 times 10 to the negative 22 grams of europium per unit cell. And we use our density to get to our length unit. So, or our volume unit, cubic volume unit, I'm sorry. And this is 9.60 times 10 to the negative 23 centimeters cubed per unit cell. Didn't mean to change my ink color, but I did. Okay, so step 3, again, edge length equals A, which equals V to the 1/3. And so this is V. So we'll take the cube root of that. And that will give us A. So A equals 4.58 times 10 to the negative 8 centimeters. Or converted to picometers, 458 picometers.